All right, well, I guess we'll go ahead and get started. Good morning, everyone. Thanks for coming to the latest installment of the Bureau Seminar Series. I'm personally excited to see this talk. I was just talking about how someone in a completely random conversation was talking about this work that's being done. So I'm really interested to see. So it's our pleasure to have Yangkang Chen here today. He is a research assistant professor and lead of machine learning artificial intelligence research at TexNet. BEG, JSG, right? In 2015, Chen graduated from the Jackson School with his PhD in geophysics. Since 2021, Chen joined TexNet as a seismologist. Chen is interested in computational methods that can be broadly applied to seismic signal analysis, seismic modeling and imaging, and earthquake monitoring. In the past decade, Chen's research has focused on applying AI techniques to various geoscience problems. With that, I'll just drop a quick reminder. Please save questions till the end, and I'll kind of go around, I'll check the chat, etc. So let's give a big welcome to Yangkang.
Good morning, everyone. First of all, thank you very much for coming and for your attendance. Today, I will give an overview of what we have done in the past decade on the topic of earthquake monitoring using AI. Quite frankly speaking, I have been involved in quite a number of AI projects, maybe dozens of AI projects. And what I want to say is that while a lot of AI projects are just applicational, the AI in earthquake monitoring is really extraordinary, unprecedented, and one of the best. So my talk is really about to decipher the mystery inside this black box. And the whole point of my talk is Rome is not built in one day. And as we look back the journey, every bit of effort, every single step, every incremental advance, and every seemingly trivial effort matters, because at the end, they all come together to make a huge difference. Okay? So the lesson is that we should never overlook this tiny bit of work, because at the end, they will pay off. So I would like to first acknowledge a couple of very important collaborators in the beginning, and then I'll show some really groundbreaking results using AI. And then I'll guide you through the long journey to these groundbreaking results in production AI at TexNet. And then I'll show you some testing results using EQCCT, our AI model, in a real-world application, just to show its robustness. And then finally, some conclusion. First of all, I want to thank a number of colleagues, collaborators, students, and postdocs who made a great contribution in this journey. And without their day and night effort, continuous support, and this talk is impossible. So thank you very much. And here I especially want to thank the whole TexNet crew. I cannot put all these guys here, but they all made like indispensable contribution to this journey. And here is groundbreaking results for our near real-time monitoring in Texas. And we have put our AI model in production for near real-time in West Texas. And here, I want to clarify that the concept of real-time is definition dependent. If we define real-time as a scale of seconds, and then we are still near real-time. But if we define the real-time as a scale of minutes, and then we are already real-time, right? So all the framework, automatic framework can be done within minutes. So that's a magic. And on the right-hand side, we show the error distribution. So the error distribution, error is measured between the AI output magnitude and the manual output magnitude. So as we can see, most of the errors are centered around zero, meaning that the error really, really small. And on these figures, we show a correlation plot between the AI output magnitude and the manual output. And we can see for the relatively large magnitude, they are almost the same. They align very well along the diagonal. Okay? And what's worth mentioning is that for magnitude above 2 earthquake, the recall is 100%, which means that for magnitude above 2 earthquake, we do not make any mistake. That's amazing. And this slide shows a dramatically improved detectability using our AI model. So here, On the top left, we show three scenarios. One is the red one, and red one means TexNet results catalog, and the yellow one and the gray one. These two ones are automatic methods, but one is traditional automatic method, one is AI methods. So as we can see, from manual to the traditional state-of-the-art of automatic picker to the latest AI architecture, we obtain a step-by-step change and improvement. Recall that this y-axis is actually in logarithmic scale. So although it looks like these two are not differing too much, actually they differ by 10 times. Right? So this is really a big change. And on the top right figure, we show the daily distribution of the earthquake events. The same thing, the red one is TexNet, and the yellow one is the traditional, the state-of-the-art automatic picker, and the green one is the AI model. As we can see, traditionally, every day we may detect manually 7 earthquakes, and then for automatic method using STA, LTA, the state-of-the-art traditional, and we are able to detect less than 100, let's say 70, but using AI, we are able to detect more than 3 or even 400 earthquakes per day. So that's a dramatic change. And here we show the magnitude distribution across each day of this month, and we see that. So for the red one, it mainly on the top, so meaning a relatively large magnitude, and the yellow one are in the middle, which is like between magnitude 1 and magnitude 2, and for the gray one, really very, very small earthquake, right? And you may wonder what happens on this day. So we have like abnormally high seismicity on this particular day, because on this day we have our Texas have a magnitude 5.4 earthquake on this day. So we have like a huge number of aftershock and small earthquake. And here I want to clarify a little bit the problem. So what we are doing really to detect the P wave and S wave from a 3-component seismogram, right? So the P wave and S wave are 2 important phases of seismic waves. So they are really all the information we detect for these problems. And based on this P wave and S wave arrival times, we can do all the analysis, imaging, location, inversion, etc. And we use STA, LTA, as I mentioned, the best of the traditional, and the clustering method, deep learning, picker, I will explain a little bit step by step. And then from this slide, I'll guide you through the long journey. So the figure is this one. Probably you still remember this news. So the ongoing AI boom really started from 2016. In early 2016, the company DeepMind made a stir by announcing that their AI player first be the best human player for the first time in history. So that news really ignites the curiosity of the whole world, including mine. At that time, I was a distinguished postdoc at Oak Ridge National Lab. We were doing a very ambitious project. We want to invert the Earth's interior structure of the whole planet, right? By using full waveform inversion, we can like fine-tune the structure, get high resolution of the Earth's picture, right? And the full waveform inversion is really an iterative process. We solve this trivial problem trying to fit observed data by iteratively updating the current model and by simulating the seismic waves to try to fit this observed data, right? But to optimize this process, we really need to carefully select data because we want to scale it up to more than 6,000 magnitude above 6 earthquake. We use all these earthquake waveforms to do the inversion, so we really need to make it automatic. So it brought me the first AI problem in seismology to detect the seismic waveform from these very random, very noisy seismograms. At that time, there are really nothing available for earthquake detecting. And so I have to develop a method from the scratch, right? So I come up with the idea of using predefined features. So these features are shown in this slide. We defined 5 features, more or less measuring the distance between the observed data and the the synthetic data, right? And this is also kind of a physics-based method. So based on these predefined features, we calculate them, and then we fit them into a multi-layer perceptron neural network shown in this slide. So this is really the very basic version of the neural network. And we feed into the neural network, and we output a decision, whether a window or whether a waveform is earthquake or non-earthquake. And back in the day, we really don't have any libraries to do earthquake detection because it's early 2016. So I need to write a library from scratch. So here is a screenshot of the library I wrote for this project. And as we can see the first committee happened 8 years ago, right? That's just when I started my postdoc. Right? And on the right-hand side, so a screenshot of the class of neural network we used to solve this problem. Right? That's 8 years ago. And then applying this approach in real data actually works pretty well. And we compared with the state of the art, which is the FlexWing method. FlexWing method is a sophisticated workflow to detect waveforms using non-AI approaches. Right? And we compare with the state-of-the-art approach at that time, and we found that the performance is comparable. And for some cases, we even detect better, like previously missed waveforms. So it works better than the state-of-the-art. But for software development or methodology development, we really need to be ambitious. We need to be picky on the existing methods. So what's the advantage and disadvantage for the first method I developed? Really need to think carefully about that. So the advantage is that it works quite well, right? But the disadvantage is that it relies on the calculation of synthetic data. It's not the pure raw data solution. So we need to think about a better solution. For example, the clustering method. So clustering really means to split a group of objects into different groups where the internal objects are quite close to each other. Right? So based on the clustering method, we define several features. One is the mean, one is power, and one is ST-LTA. So here I want to mention that ST-LTA is the state of the art for earthquake analysis, because it's very effective, and it has been used for decades for traditionally detecting the earthquake from three component seismic grounds. And here we also use the ST-LTA as one feature in the clustering approach. So these three features, just like the two coordinates for this coordinate system, so X, Y, Z, but in here, we also have the Z components. So we have three features, like high dimensional space. We want to cluster all these waveform points into different groups. Right? And here, we show a simple example between the clustering and the ST-LTA method. We see that the clustering method seems work very accurately in pick the P wave and arrival, while the ST-LTA method made a mistake. So here is why on the right-hand side, we show the exact feature, mean and power and ST-LTA. We found that the feature of ST-LTA actually made a lot of mistake. We create a lot of abnormally high values, so which caused the problem here. Right? But by using other features like mean, like power, we really can smooth the data a little bit and make a better decision. Right? So this is the principle of the clustering-based method. So we apply it to real data. One is the microseismic data, and one is the earthquake stack data. And for both cases, it works pretty well. And compared with the ST-LTA method, it works much better, much more beautiful. The red circles align very well with the waveforms, right? And it's even better, even more beautiful for this earthquake stack. And we keep being more ambitious. So previous application just to pick the arrival, but we also need the waveform so that we can do full waveform inversion and for imaging, waveform-based imaging problems. So we further modified the clustering method to include more features. For example, the spectral central features calculated in this way. So here we we removed the STLTA feature because STLTA feature really highlights arrival information. But in this case, we want to highlight the information of the waveform. Right? So we defined a slightly different features, but in the same way, we can classify the waveforms into signal and the noise. So for example, here we have clean data, we have the noise data, we have the clustering, we show very beautifully detected waveforms, right? Based on these detected waveforms, we can do better imaging applications. So on the right-hand side, we show an application of real-time microseismic imaging using these automatic detected waveforms. So here is original scale. We see those the windows, those detected waveforms are very reasonable, and here is a zoomed view, and below are two imaging results. These energy clustering correspond to the microseismic event location. Right? So traditionally, if we use all the data, we might obtain a scattered location results, while using the carefully and automatic detected waveform, we can obtain very high resolution microseismic location results. Right? And we keep moving on. So in previous work, we use 3 features, and then we keep including more features. So here we do a very ambitious trial. We include 191 features into this framework, and using an even better approach called support vector machine to better classify the waveform into signal and noise. And here, all these 191 features are more or less physics-based. They have a specific physics or statistical implications. So the reason why we come up with this idea is that it is inspired by the sound classification, voice classification field. So they have used all these features for a long time. So we take advantage of this idea and then make our problems more solvable. So here is the example. So we have for this approach, we have the training data, we have the label, and here we also show the heat map, basically show the relation between different features. And here we also show the importance of different features. We see that although we have like almost 200 features, but they are significance are different. Some features are more important, and we show here. And below we show a testing results. For example, for this testing field data, that's the input. And for 1D and 2D features, we obtain quite different results. So for using 1D and the 2D features, we get obviously more spatially coherent results, while the using 1D feature only, we get some scattered results. But anyway, so it is also one step in the long journey. And then we keep moving on. We tried the convolutional neural network because the previous approach are really shallow learning approach, while the CNN convolutional neural network is really a deep learning approach. So we also try the CNN approach. So, but first I want to show two comparison for the for two data. One is with a relatively higher signal-to-noise ratio, weaker noise. We can see that for the clustering method I mentioned previously worked pretty good, pretty well. And on the right-hand side, actually, when we increase the level of noise, actually the clustering doesn't work. But using the CNN decade approach, we still find a very good result for the arrivals. So next slide, I'll show the principle. So here, suppose we input the seismic data, and then we feed it into a very basic convolutional neural network, and then we do some feature extraction, and then do some feature mixture, and then make a decision, right, for non-wave or wave components. And on the right-hand side, we show a workflow of how we apply the CNN in these problems. So there are 3 vertical flows. They correspond to different approach. The first is the STLTA method, and in the middle one, we show the clustering method I mentioned before. And on the right-hand side, we show our CNN framework. So we do not use the CNN directly, like many others. We combine the CNN with the clustering method, because the CNN really can just define a window a candidate window into waveform or non-waveform, it lacks the resolution, the temporal resolution. While using clustering, on top of that, we can first get the anti-noise ability, but also we get the high resolution, right? So that's really the principle of this CNN and clustering method. And this slide shows some results. For example, this is the how the noise level affect performance for different methods. So this green curve show the signal to noise ratio variation curve. As we can see, we gradually increase the noise level and resulting in a lower signal to noise ratio. And for the red curve and the blue curve show correspond to the errors for the clustering method and for the CNN clustering method. We see that even for very low quality data, we can still obtain quite low error for the CNN-based method, right? Much better than the red one, right? On the right-hand side, on the middle and right-hand side, I will show the synthetic example and the real data examples using these two methods, and consistently with that, the CNN clustering method is way better than the clustering method because it has a higher anti-noise ability. So, and probably you have heard the time frequency analysis assisted deep learning. So here we explore the benefit using time frequency transform for helping the deep neural network make a decision. So this slide really shows the principle of why we should use time frequency analysis. So for example, we show different seismographs with different noise level, right? From left to right, we increase the noise level. And we found, and we also plot the time frequency transform. Here we use the continuous wavelet transform. And we really found that even though we increase the noise level, we found that the low frequency part of the time frequency map are quite consistent, right? And the only difference is that for the high frequency part, so the high frequency becomes more and more random, right, in the time frequency domain. So that's really the principle of using time frequency transform, because we can better distinguish signal and noise. Noise mostly reside on the higher frequency band, right? So that's the main point of the the time frequency transform for deep learning. Right? So here I show the general framework of using further, including time frequency transform for doing the waveform detection, right? So we feed in the seismograms, we do the continuous wavelet transform, and then based on the 2D wavelet transform domain, we extract the features that become the 2D features, right? So that's really what the CNN is good at, right? We extract the 2D feature and then make a better decision. And the right-hand side, we show the ground truth data, which is prepared by a human, and then we show the deep learning result without the CWT, without time frequency transform, and show the result of this framework. We show that the result is much better than the earlier cases. Okay. So it seems that we have tried a lot of methods, right? And it seems that all these methods work well in certain cases. But what's the remaining problem? And the remaining problem is all these models are not generalized, right? So we use the very local data set to train the network. We really do not apply it to very large data set. And of course, we cannot get the very generalizable performance. So think about all this previous research, what is still missing? So that is the data. Right? So data is very important. Then starting from 2021, we started gathering a huge amount of data for training a very generalizable workflow. So here is the first attempt. So here we use a very deep neural network based on convolutional filter. So as we can see, it is very deep and it contains more than 24 million parameters. So it's a very deep network. And then we call it scalar. Why? Because it's based on continuous wavelet transform. Because as I said, continuous wavelet transform can help better distinguish between signal and noise. But there's a disadvantage of the traditional continuous wavelet transform because it adds more computational costs. So the compromise is that we only use a few scales. For instance, in this case, we use 7 scaled in the based on the continuous wavelet transform, so that we can get reasonably cheap computation. So because we use continuous wave transform, the input of the data are 3000 by 7. 7 is scale, by 33 is the component number of components, right? And we surprisingly we obtain very generalizable performance. It is almost applicable to everywhere in the world, right? Like Japan, like Egypt, Texas, and Arkansas, right? And this work is published in JGR in 2021. And here is just a few examples of how it performs on very different data sets, different results, right? Different data set. So for example, this is for like a short duration event, right? And this is for like very noisy events, and we'll see the signal is much weaker compared with the first one. And this is for the case of one channel malfunctioning, right? And this for a longer duration event. We have a longer duration of this event. And this one is very interesting. This is a very noisy case, but we obtain the better result even than the ground truth, right? Because the ground truth is really not the real ground truth. It's prepared by humans. So in this case, we actually perform better than human. And this is the another malfunctioning channel. In this case, the NOS component. And this one is for static seismic. It's not only for local earthquake. And this is for one like segment containing 2 events. So in this case, we have 2 events. And in this case, we have 2 malfunctioning channels. So for all these very diverse cases, we perform very well. Right? And here we also highlight the data. The data is from North California, Japan, Arkansas, Texas. We use all the huge amount of data, very diverse for training, validation, and testing. So it can be generalizable. So here we show a benchmark comparison with several state-of-the-art approaches, right? So first to our fast method and the template matching method, we can see the comparison between catalog and the method we choose for comparison, right? So the first 2 are pretty good because they are based on template. So which means that for a certain area, certain application scenario, we use a template to do cross correlation. And then it's no wonder we can detect way more earthquakes than others. But this template-based approach is not generalizable. It's only applicable to certain areas. And this is our result that compared with catalog is pretty good. And this one trade is the deep learning based. At that time, kind of the best. And it is also the early version of the later on famous transformer architecture. This architecture is called CRED. And the other 2 results are from SDA-LTA with different implementations. And we can see that compared with other automatic methods that can more or less generable, our method is best. But compared with template-based method, it seems that a little weaker. Right? And then we keep moving on. At that time, 2021, it's about the time when the transformer started dominate the AI world. And so we started some attempts using vision transformer. So in this case, we not only pick the P wave, but also we want to like predict the magnitude. So that's a very fast response. So we developed this framework, inputting the 3 component data. We automatically pick the P wave, and based on the P wave, we create a segment, a waveform segment, and then do the magnitude estimation, and then we can output the P wave arrival and the magnitude simultaneously, right? And we apply this framework to California and Texas. And here are the magnitude performance, a magnitude comparison between predict one and the ground truth one. And for both cases, our magnitude prediction very accurate. Right? And here I want to mention a little bit why we use P wave only, right? Because of earthquake early warning. Because an earthquake early warning every second matters. So the goal of earthquake early warning is to issue an alert before the most destructive S wave hits the ground. So every second matters. So we are really not allowed to use S wave. Right? And the interval between P wave and S wave can be up to 10 to 20 seconds. So we really only rely on P wave. And for facilitating the earthquake early warning, we develop a systematic detection magnitude calculation and the location framework. Right? So the idea of this location framework is simple. Right? Suppose we have a huge amount of data such as Japan or California, and then we can train an automatic model to predict the location after an earthquake happened, after we detect the P wave. Right? If we do not have such high amount of data, and then we numerically generate data for case of Texas. Right? So that's the basic idea. So here we show the case study in Japan. And the left-hand side, we show the general framework, basically what I have just explained. On the right-hand side, we show how we split the catalog events into like training and testing. Right? And we know that the Japanese network is crazily dense, and we have like crazily high number of recorded seismic events. So we have a huge amount of data for training, so we can obtain a very good result. So here is the result. So here is a result of the location prediction. So we zoom in this part to here and here for a better view. So here we see the triangle are the station, and the red dots are the catalog, the ground truths, and the blue circle are the predicted one. And those black lines correspond to error. So the shorter, the better. Right? So in this case, we found that most of the cases, the blue one and the red one almost overlapping each other. So the prediction actually pretty high. And we unsurprisingly found that for different areas, for example, for inland area, we have a relatively small prediction error because we have higher redensity. And for like coastal areas, we have a much smaller redensity. We have a relatively higher error. So, but that's just for earthquake early warning. For daily earthquake monitoring, for example, in Texas, we use we need both P wave and S wave. So that's why we developed later on the latest AI-active EQCCT. Right. So simply speaking, we have such complicated AI workflow and the architecture. And it is still, again, very general. It can be applied to almost everywhere in the world. And later on, I will show even more extreme cases. And for the CCT stands for compact convolutional transformer. And in this case, in our training, we separate P wave and S wave training process because it's difficult to obtain the optimal performance for P wave and S wave simultaneously. We need to separate the training so that we can get the best result for both phases. And so simply speaking, for the benefit of the CCT architecture, it is faster than the transformer network, and it is better than the convolutional network. So that's the whole point. And it is a lightweight architecture, right? So with a very lightweight architecture, we can be very general. That's very cool. So very important question, why EQCCT? Because the simple answer is because we almost tried every method we could try. Right? So from 2017, very basic multi-layer perception, the latest architecture, we try everything we have tried. Right? So I have introduced some of them, and I also do not mention some of them. For example, the capture network is also one of the advanced AI architecture, but I just don't show it here. So the whole point of this process is that for obtaining a very groundbreaking result, it takes time, right? And every bit of this effort matters, right? And if we try all of them, and then we know why they succeed, why they fail, we know why the latest method is the best. So that's simple. And here is a slide to show very simply the basic, the principle why a transformer is better than the convolutional neural network. So I like use this example, this face recognition example. So what the CNN is really doing is that for a human face, if we can successfully detect those key components like the eyes, nose, mouth, or even ears. And if we detect those components without their relationship, and then we can make a correct decision for convolutional neural network. But of course, it's not enough. But by transformer, we not only detect those components, we actually detect their internal relationship. So that's the difference between the transformer and convolutional neural network, and why the transformer architecture is way better in many seismological problems. And then I will show a number of testing results using our latest, the best AI model. First, I want to show some, show the generalization of performance for different cases of seismograms. For example, for this case, we have a relatively large magnitude, pretty clear signal for two waveforms. And here I want to explain a little bit. So for each peaked event, peaked phase, we show both the AI output and the manual output. And if these two lines are overlapping each other, that means they are exactly the same. So for some cases, you can see the slightly shaped, slight difference. So that's normal, right? And for both cases, we found that these two lines are almost overlapping each other, corresponding a very good performance. And then this is another case, relatively small magnitude, still quite high signal-to ratio. We still can see the signal. And for these two cases, these two lines are still overlapping each other. And this is a relatively more noisy case, and we can still do a pretty good job. And this is the error distribution comparison for different competing methods. So here I show the two most representative deep learning-based picker, TexNet and EQ transformer, and we want to show the advance of our latest AI model compared with these two widely used models. So simply speaking, so these errors correspond to how the errors are distributed around around zero. So if the histogram is more centered around zero, and then that corresponds to a higher accuracy. So as we can see, so the histogram becomes taller and taller and more centered around zero, meaning that our EQCCT performs best. And for the top one, the P wave, and the bottom one, the S wave, right? You obtain the consistent performance. And here from this side, I will show several applications in very different areas. The first area is Japan, right? So let's see how it performs. And the Japanese data set actually quite high quality. So in this case, we performed quite well. These two lines are almost overlapping each other, right? And the next case is Texas. Texas is more noisy because we have most of the seismicity are from oil and gas operations. So in this case, we still performing very well. Right? I'll just go through this example very quickly. And this is the Italy result, and we still perform very well. And here is the error distribution for P wave for different location, Japan, Texas, and Italy. And for each cases, each areas, we have the better error distribution, the smaller, much smaller error, right? From here to here to here. Right? And this is the error of S wave. And this slide is a very interesting application for microseismic. So microseismic has a dramatically different sampling rate. So for example, normally, for broadband seismometer, in the training data, we use 100 Hertz sampling rate, but for microseismic, it can be up to 5,500 or even 1,000 sampling rate. So the sampling rate is very different, and mostly the microseismic data events are caused by hydraulic fracturing, right? So actually, we have very limited training samples in our training database, and their geographic location is also very very special. In this case, West Canada. It's of course not included in our training database, but very surprisingly, we still obtained a very good result for this microseismic application. Right? So that's very encouraging. And here I show a choppy data application. So by choppy data application, I mean that we do not apply it on continuous data. We, according to the catalog we already have, we segment waveforms. And we know the waveforms have the signal. So then we apply the AI model just to pick the arrivals and then do the location to verify how the picking will affect the location performance. So here is the example in Midland. So First of all, for almost 200 events, we have most of them, we have very negligible error, but only a few of them we have like an outlier location, right? So this is very, very illustrative because we know that for the majority of the events, we have very accurate peaking, very accurate location, very robust, and we still have some outliers, right? So that's actually very illustrative for us. And then we want to apply it to continuous data to try to create a very highly complete, high resolution cataloging near real time, right? So here is a workflow, right? From the component of the data to EQCCT peaker and then the peaks. And then we do the first location, second location. The only difference is that we use a different velocity model and we have a better depth. And then we even do the relocation. Relocation can help us to detect more fault structures. Now here is the magnitude distribution and daily distribution I have shown in the beginning of my talk. And here is a comparison between the first location result and the refined location result. The only difference is we use different velocity model. And we can see that for different amounts, so each panel denotes 1 month's detection results, right? And using different velocity model, we found that actually the catalog is more clustered. Right? So we can see the resolution improvement. And here is the relocation comparison. So the left-hand side is TexNet result, and the right-hand side is the AI results, right, for 1 month. And the top row show the result, the catalog before relocation, and the bottom show the after relocation. Right? So first of all, we see that after AI, we detect way more earthquakes, like almost 50 times more earthquakes than the traditional manual effort. And secondly, after relocation, we see a beautifully aligned fault structure on the surface, right? So that's the magic of relocation. And here I show several like waveforms, just to show how the peaks on the waveforms. So here is an example. Here's the event detected by TexNet. And here we use AI. Of course, we also detect this event, but we detect this event from more stations, right? And for most actually detect triggered station, we have like a much noisy signal, noisy data quality. So which means that for the relatively high amplitude, high magnitude events, we can detect better, and we can detect the event from more stations, right? And make a more accurate location result. And this is the example event missed by TexNet. Right? So this is a very small magnitude. In this case, 0.38 magnitude, and this is completely missed by our analysts, but it is successfully detected by AI. And then here is a comparison between the AI peaks and the traditional STA, LTA based peaks. And we found that we detect the same event from more stations than the traditional STA, LTA peaker. And we also make the location more reasonable than this one is outlier from the traditional approach. So this also tells us we not only detect more events, but actually we detect more precisely for the arrivals. And here is an interesting study how dense network helps us to detect more earthquakes. Right? Suppose we don't have so many stations to date, and suppose we go back several years, and when we only have 12 stations, or when we only have 8 stations, and then the detectability are completely different. Right? So that's show something. Right? We need not only AI, but also a dense network. And this slide shows how the AI helps delineate fault. Right? And on the left-hand side is the depth slide from longitudinal slice, and the right-hand side is the latitude slice. We can see beautifully delineated fault structure here. Right? This corresponds to the Carlson earthquake fault line. And we detect it very beautifully, even before the main shock happens. And this is the better for delineation, right? For on the surface, on the map. Left is from TexNet, right-hand side from the AI, right? To detect like way more events and have a very clear photo delineation. Okay, so this is an interesting association between seismicity and injection. Right? So here we show the how the seismicity change daily, and associated with injection of the fluid. And we found a very interesting phenomenon. We found that the seismicity quietens when injection peaks. Right? So that's like disobey our traditional thought. So there are a lot of possibilities here. One of them is maybe the indication of a delayed triggering mechanism. Right? So a lot of things to be done thanks to the power of AI. And then we also, here is an illustration of our GitHub repository. We want to make all these framework models publicly available. So we prepare this GitHub repository carefully. And then as I said, we need to be more ambitious. We even compiled our own benchmark dataset for AI, and that is for Texas. And it includes almost all the effort in the past 7 to 8 years from the whole TexNet group. And based on this, we can obtain a much better like location performance in the state of Texas. And for example, we can detect the very far away station and using the transfer learning based picker, right? And here is the first magical figure I showed in the beginning. And lastly, I want to summarize several advantages of EQCCT compared with other pickers. So simply speaking, it's more precise and it detects way more events. And last slide is that I want to conclude several lessons from this long journey. So if you look back to the journey, we found that there are two distinct developing stages. So one is between 2017 to 2020, right? Where we lack a lot of data. And we can do something, but we cannot do very amazing things. And then in a later stage, we do a very amazing job because of the massive data. And we need a benchmark. It's very important because we do AI not just for doing AI. We need to beat our state of the art, right? So, but how to define the better performance or fast performance? We need a benchmark. We need a very specific criteria to define the success. So that's why we need a benchmark. And we need teamwork, right? And we, in the whole team of this journey, we have experts from earthquake science, machine learning, software visualization. But we need teamwork. We cannot do it all these things all by myself. And we need courage and for production and real-time runs. And here I really want to thank Alexandra's sitting down here. So for pushing this effort to in production running. So that's really, really needed courage. And so lastly, Rome is not built in one day. And every bit of the effort will pay off in the end. Thank you very much.
I learned so much. So anybody have any questions for Yangkang? I saw Sue's hand first.
I have a not very a basic question. So with the machine learning, you're detecting a lot of the smaller events that would have been included in the noise, right? So what is how do you even qualify what's noise and what's signal for seismicity? I mean, you said a little bit about noise. It's related to production. So that means clanking or something from production.
Very
anthropogenic or so maybe I don't know the basics of picking seismic events. What are you trying to get rid of, or what's in the noise category versus the seismic event category, and what separates them?
That's a very good question. So because this is science, and we don't know the ground truth. So very frankly speaking, we cannot tell exactly whether a very small event is a real event, but we can see the statistic from a large number of events. For example, we can plot, we can plot the frequency magnitude distribution. And we see if it aligns with the fault, predefined pre-knowledge of the fault. So that's really, there are some perspective to validate it, but Yeah, because it's science. We don't know exactly. So the noise is just not caused by the sleep of the faults. So we can basically we can do a basic definition like that. Yeah.
So can I tag on to that question real quick and then I'll pass to you? So I also I like to ask dumb questions because that's who I am, right? But I was just curious, if I remember your slide correctly with the error distributions, right? It seemed like, if I remember correctly, you had a higher error distribution with the really small magnitude events.
Yes.
So my two-part question is that mostly just because in a sense, the signal to noise ratio is so low with the small magnitude events?
Yes.
Yeah, okay.
Yeah.
And then second part of the question is, I mean, I want to say, isn't that where we're seeing a lot of the activity in West Texas? It's a lot of, we hear about the big ones, right? But there's a lot of little ones out there too, right?
Yeah.
So is there any effort to try to improve that picking on the small scale of the seismicity?
Yeah, that's a good point. So that's why we compile our own AI dataset in Texas. So that data is specific to Texas. So we have the characteristic of the signal and noise of state of Texas. So then we can do transfer learning based on this globally generalizable model, and then we can do a better job for local application.
Yeah, Yangkang, you said you put the code in GitHub.
Yes.
So I'm wondering if you get any notion in terms of how many people actually download it, use it. Do they give you feedback? I would imagine a lot of people all over the world are interested in this. So do you get some feedback on this?
Yeah. We can get the sense of that from the feedback we received through email. And we can also have an idea of the popularity through conference, through networking. We know how others are using our product. So through different ways. Yeah, I don't have a very specific clear number of how many downloads it had. So yeah.
Hi, Yangkang. I would like to ask you about what do you think is the future for AI in earthquake detection and phase picking, specifically about, we know that there is a limitation because the data is manually labeled, and so
Yes.
the results can be as good as the data.
Yeah.
And what are the strategies or techniques that can be done to overcome this?
Very good question. So as I mentioned always through my talk, we always need to be more ambitious. So the current result is definitely not the holy grail. So we have a long way to go. For example, so current training is based on supervised learning, and eventually we will go unsupervised learning. Which basically we need to mine the information, mine the feature from even more 100 or 1,000 times more data from themselves, and then we mine the feature, and we can just like the large language model, right? And we can based on some strategy, we can learn the features from the data, from way more data automatically without a human labor, right? Because based on human labor, we have limitation. That's need to be a relatively large magnitude, right? And that's one part. We need unsupervised learning, and on the other hand, is that for almost all the existing application of AI for seismology are based on broadband seismic data. And we have actually way more data. We have in the era of Internet of Things, we have way more data. We have sensor everywhere. Like in your phones can be a sensor to sense the seismic waves. So our eventual goal is to leverage all the sensors, or at least the seismic sensor, geophysical sensors, to have a better understanding of real-time status of the Earth. So that's our eventual goal, I think.
So first of all, let me thank Yangkang for the nice presentation, and I would like to thank also the analysts, because all these data used for the training are provided by the analysts. So it's like 70 years of data. Thanks. And I would like, can you go to slide 56? I would like just to add a few things because Sue mentioned the noise, so that's critical. The noise, when we use training data for AI, we didn't include only the earthquake data, we include noise data. So we said to the training data set, these are the earthquakes and those are noise. So the training system could understand the differences. And when it does the evaluation, it can define that this is noise or this is not noise and this is an earthquake. So you can see the P&S peaks that Yangkang mentioned. But I would like to go back to this. So here you have the red is the web catalog, what we publish on the web. Yellow is the one we have on our database with the traditional method, and gray is the AI. So that the changes you see are becoming high, especially in lower magnitude earthquakes. So like 1.5 and less, you see the high difference between the classical approach and the AI. And this is because the classical approach, we know they fail a lot when there is a high noise level. So that's the key thing here. So in order to change that, you need two things. One is to densify the network, as Yangkang said earlier, and the other is that you need to have very good recordings. Even if the network is not dense, then you have to have, you use other techniques, we do powerful stations, things like that. But all these things are important for AI. So that's the key thing here. And one last thing to add, as Yangkang said, it takes a lot of courage to start this work, but now to move to production, because all this work has been like in near real time. It doesn't work until now at the real time level. So every few minutes we try to calculate all this information and put it on the system we have. But now we have a new group that is working on moving things into real time. And that, I think, will be the big advantage of making use of the AI on the real-time world. And when I'm talking real-time means as soon as the earthquake is happening, in less than a minute, you get the information that goes to the system to detect the event, which is like, it doesn't happen up to now. Up to now, it takes minutes to detect an event. That's why USGS takes a few minutes to have those information available, and we're supposed to provide this information in 20 minutes from the time of the event. If we decrease this time from 20 to 10, having AI as an additional tool, I think that will be great. That's the big advantage of those tools, to use it on real time.
All right, well, we're pretty much out of time. Thanks again, Yangkang. Thanks again for everybody for coming. Or did we get a quick one online finally? We've got 2 minutes left. When you say an early warning system, is there a probability assessment in early warning?
I think for early warning, it's a real event. So the real event has happened, and then we provide a very fast characterization about the source and providing a early warning that the seismic, the most destructive S wave is imminent. So it's coming. So just take immediate action to protect yourself.
Got it. Thank you. See y'all next week.